and let me open the case 1 file, and it has all the information for the test condition. And let me open the case 2 file, and actually I can copy this and go back to the case 1 and paste it here. So now I'm getting a report of the various positions. So notice the tolerance range, which is the sum of the tolerances, and is changing as the mechanism position changing. So like this, we can quickly do a lot of measurements in, maybe whatever you wish, because the process is pretty fast. You can look at the mechanism in 10 different configurations and save the results, and then you can then make a informed decision on how much tolerance to allocate to that point so that it will work within the whole range. And because you're doing the tolerance analysis in the conceptual stage of the design, it can have a tremendous effect on the overall cost and performance of the product, because you can order your tooling first. You can also check your manufacturing capabilities up front, and this becomes especially useful if you're going to outsource the manufacturing, so you can validate a vendor. But now let's look at a situation when reverse tolerance analysis is required. Let me close this. So here, a manufacturing engineering got a drawing. This is in GraphicCalc, but this could be a drawing in any CAD application. And the manufacturing engineer has to make this part. This part has got a pin here that has to be welded, and then these two holes have to be punched. And so the manufacturing engineer knows that he can hold this center of this true, but then this will have a tolerance. So what the manufacturing engineer can do is, supposing he got this as a CAD drawing in any CAD application, he saves the geometry in the DXF format, and then he reads in the DXF file here. So this is the critical dimension that he needs to satisfy, which has got a tolerance allocated of plus minus 0.25. So now he says, okay, I'm going to hold this to 0, but my machine will have a tolerance in the X and Y direction. So he defines the tolerance vectors to simulate the process. So the nominal value of this length is 90 millimeters. He's constraining the tolerance chain. And nominal value of this is 25 millimeter, and this is located at the end of this line. Now he's selecting his manufacturing processes, so he thinks, okay, I can punch this. The welding machine has a polar tolerance. It'll be off center, but let's say 0.1 millimeters. Immediately you can see the effect on the critical measurement here. It's almost similar to watching a virtual manufacturing process going on. Then he selects this vector, and the length is not going to be 90. The machine has a tolerance of plus minus 0.25 in its travel. I'm just putting these tolerances a little exaggerated to show the case. And likewise, this one also will have a tolerance. Notice the tolerance gets propagated, so you don't have to re-enter if the tolerances are the same over multiple vectors. And let's say this is also because of the fixture going to tilt by 0.1 degrees. Very well. So he has the simulation of the manufacturing process. Then he clicks on the dimension of interest and says analyze my tolerances. Here the engineer will use the uniform tolerance, because when you select uniform tolerance, the results are given in a different format. So here the result, The tolerance and the sigma level are fields that you can enter values. So this is the standard deviation of that dimension. But he enters the tolerance that is specified in the drawing, which is plus minus 0.25. So that means the full tolerance is 0.5. And GraphicCalc tells the engineer, manufacturing engineer, that this will be the reject rate. This will be the quality of the part. So now he has a choice. He can either use a more expensive, more accurate manufacturing process to meet the tolerance goal as specified in the drawing, or he can simply enter the desired quality goal here, 3 sigma, and he can call the engineer who designed it, look, if you want really 0.25 plus minus tolerance, it's going to be an expensive part. But if you can loosen your tolerance to 0.3275 plus minus, we can make this part really cheap. We believe this is a capability which is currently missing in the industry. There is no ready tool available for manufacturing people to mediate with the design engineers upfront with tangible proof, rather than making actual physical prototypes or making a small manufacturing run. So this is critical to make sure that the design can be manufactured cost effectively before you finalize the tolerances, and this can have a significant impact on the overall cost and performance of the product. So with a little bit of practice, this will become like a second nature. As soon as you put two parts together, you can very quickly check the tolerances. You can also attach the calipers or the calculation to measure any part, any point of interest. For example, I want to know where the y coordinate of this is going to fall. So as the tolerance is going on, it's telling me the y coordinate. I can analyze and allocate tolerance. Maybe there's a pin which is going to pass through this here. Or I can, for example, it's critical for me to have the center of this, and there is a distance from the midpoint here going up here, and it's perpendicular to this, and it's terminated by this. And I want to know what is the effect of tolerances on this critical measurement. So you can attach the calipers to anywhere that you wish and measure the linear, angular, and radial dimensions, as well as use all the graphical calculation built-in functions to extract values from the model, and then apply really fast Monte Carlo analysis to a part to see if it can be manufactured, or to an assembly to make sure it will work as expected. And a good mediation can be done between the frequently conflicting goals of design engineers and manufacturing engineers, because the design engineers would like to give the tightest tolerances and manufacturing engineers want the loosest tolerances. So GraphicCalc here becomes the mediator. Thank you.